Right, so let us now solve this exercise. So what do we have to show here? There are parts of this exercise. First we have to prove these two equations, and then we have to conclude that the function f inverse is an invertible function and its inverse is nothing but f. So let's first show this one. So this has to be shown to be true for all x belonging to x. So let x be any element in x, and let us denote this element f of x by some symbol, say u. Then by the definition of f inverse, what is f inverse of u? F inverse of u is nothing but x. Hence, f inverse of f of x is u. That's what we have. We are denoting fx by u. So this is nothing but f inverse u, and f inverse u is x. So that's how we prove the first one. Okay, so this one is over. Then just like that we can prove the next one. We can write if we want, hence one more line. F inverse of f of x is equal to x for all x belonging to x. Just to emphasize the fact that this is true for any element x in capital X. So the next one will be similar. Now we consider an element in capital Y, and we denote this element f inverse of y by v. Note that f inverse of y makes sense because y is an element in y and f inverse is a function whose domain is capital Y. So then f of v is equal to y. Hence f of f inverse of y is equal to f of v, which is equal to y. So f of f inverse of y equals y for all y belonging to y. So the first two things we have already proved. Now we have to conclude from this that f inverse is invertible. First that, and then we have to prove that the inverse of f inverse is nothing but f. Okay. Note that the equations this is equal to x for all x in x, and f of f inverse of y is equal to y for all y belonging to y, imply that the function f inverse composition f from x into x is surjective and the function f composition f inverse from y into y is injective. And why is that so? That is because you can see that these functions are nothing but the identity functions on these sets. They map every element onto itself. Okay, so the identity map on any set is both injective and surjective. So both of these functions are injective and surjective, but for now we need surjectivity of this one and injectivity of this one. Okay. Hence, by the previous exercise, f inverse is both injective and surjective. That is, f inverse is bijective. And hence is invertible. Okay, what did we have in the previous exercise? If you recall, the previous exercise has two functions, f and g, like this. F was a function from x into y and g was a function from y into z, so that we can form the composition. Now, if g composition f is surjective, then G is surjective, and if G composition F is injective, then G is injective. So that exercise, am I saying it correctly or have I said just the opposite thing? Let me just see. Okay, show that if G composition, yes, if G composition F is surjective, then G is surjective, and if it is injective, then F is injective. Now you look at this. This is surjective, means F inverse is surjective. So that's how we are getting surjectivity of F inverse. And this is injective, means F inverse is injective. So that's how F inverse is also injective. And that's why it's bijective, and which is nothing but invertible. Okay, so that means there is an inverse. Now finally we have to show that this inverse is nothing but F. Okay. Note that, okay, what is the domain of F inverse? Y, and its range is X. So if we take its inverse, the domain of that inverse will be X and range will be Y. Note that the domain and range of F inverse are X and Y respectively. So that means this equality that we are trying to show now, the first condition is true for this equality, that both these functions have the same domain and same range. Now we have to show that they do the same thing to every point in the common domain. Now let x belonging to x be any element then should I write there exists or should I proceed like this? I think it's better to proceed like this. Let me use another name. Let W be equal to f of x, or I could have taken y also. Okay, let me take y. Let y be equal to f of x. Then f inverse of y is equal to x. Okay, now note that since we have proved that f inverse is invertible, we can use the definition of its inverse, and according to that definition we have this: f inverse x is equal to y. Okay, because we apply f inverse on x, we will get y. That's because f inverse of y is equal to x, and we are not talking about the inverse of f inverse. Okay, so we are not bothered about the fact that this itself is an inverse. We just treat it as a simple function. That's all. Maybe gy is equal to x, so g inverse x is equal to y. This implies is equal to y, but y is what? Fx. Hence and this ends the solution. Okay, so this was the solution to the 6th exercise. Okay, so now next we have the 7th one. So this one says let f from x into y and g from y into z be functions. Show that if f and g are bijective, then so is G composition F and we have G composition F whole inverse is equal to F inverse composition G inverse. So we are given two functions here, and we are first of all asked to show that if these two functions are bijective, then this is bijective. We have already mentioned this in one example, in one exercise. And since it is bijective, after proving its bijectivity, it becomes invertible, so it will have an inverse, and its inverse is equal to this. The order of the functions changes. So this is what we have to show. So the first part already follows from exercise 332. Okay. So let us first mention that. It follows from the second exercise that if f and g are bijective, then G composition F is also bijective. Okay. Next, we prove this equation. So like any other case, first of all we have to make sure that these two functions on both sides, they both have the same domain and same range. Okay, we are just going to mention that they have, but let us see that that is actually the case. Let's go through the logic here quickly. F maps x into y, G maps y into z. So that means F inverse will map y into x and G inverse will map z into y. Okay. So let's see where does that take us. Okay, so now G inverse, not G inverse, F inverse composition G inverse. We have to make sure that in forming this composition, the image, the range of G inverse should be equal to the domain of F inverse. Range of G inverse is y, domain of F inverse is y. So okay, we can form the composition, and it will map the domain of G inverse into the range of F inverse, that is x. And looking at this one, we find that G composition, if we already know this, it maps x into z. So that means its inverse will map z into x. So both these functions have the same domain z and same range x. So this is the first condition. This is true for us. Now we have to prove that they map the same element of z, any element of z onto the same element of x. So we will now simply mention this. Note that both the functions this and F inverse composition G inverse have domain Z and range X. Okay, so now since the domain is Z, so we take any element in Z. Let Z belonging to capital Z be any element. Then there exists a unique element Y belonging to Y such that G inverse is a function from Z into Y, capital Z into capital Y, such that G inverse Z is equal to Y. Okay. From this, we have Gy is equal to Z. But now Y is an element in Y and F inverse is a function with domain Y and range capital X. Also, so because of that, there exists a unique element X in X such that F inverse Y is equal to X, and from this we have Y is equal to Fx. Okay, so we will now calculate the output of this function G composition F inverse when the input is Z. Then what do we get? Let us see. From these two equations, y is equal to f of x and g y is equal to z, what do we get? Then we have z is equal to gy, but y is what? F of x. So this means this is G composition f of x. And we have already seen that G composition f is now bijective because f and g are bijective. So that means it is invertible. So this implies G composition f inverse of z is actually equal to x. Okay, so we have calculated the output of G composition f inverse when the input is z. Now we will calculate the output of f inverse composition G inverse when the input is z. Also, okay, I think this we can do directly. Yes. F inverse composition G inverse of Z, by the definition of composition of functions, this is F inverse of G inverse of Z. And G inverse of Z is Y and F inverse of Y is X. So these two outputs are equal. So G composition F whole inverse equals F inverse composition G inverse. This has been proved, and this is true because we have chosen this small z arbitrarily in capital Z. So this I think I can write one more line also. Thus, this is equal to F inverse composition G inverse of Z. To emphasize the fact that not only are these two equal, but this is true for any Z. Now we have equality. F inverse composition G inverse. And now the solution is over. And finally, we have the 8th exercise. This one has some subdivisions. I think 4 subdivisions. Okay, we will look at them one by one. But before that, let me refill this. I think it's running out of ink. So this is the 8th one. Okay. If X is a subset of Y, let this is the Greek. The dust is creating so much problem. Greek letter iota. Okay. And tau is also using suffix. This is the symbol for a function, iota x into y. And it's a function from x into y. It's nothing, it looks quite fancy, but it's nothing but the inclusion map. Let this be the inclusion map from x into y. Defined by mapping. What is the definition of an inclusion map? It's almost like the identity map. The only thing is that in identity x and y are equal. In inclusion, x is a subset of y. The rule of assignment is same. That is, any element in x is mapped onto itself by mapping x onto x. For all x belonging to x. That is, this is defined to be equal to x for all x belonging to x. This is the definition of the inclusion map. Okay. And okay, in a previous solution we have mentioned identity map, right? But in this book, it's now only we are going to introduce the identity map. Anyway, you know what it means. The map from x into x, if this x and y are equal, they can be, right? Because x is a subset of y, not necessarily a proper subset. The map in particular is called the identity map on X. Okay, and now come the subdivisions. A, show that if X is a subset of Y and Y is a subset of Z, then inclusion map from Y into Z, composition, inclusion map from X into Y equals inclusion map from X into Z. So this is the first thing we have to prove. Then subdivision B. Show that if f from A into B be a function. A is any set, B is any set, and f is any function with A as domain and B as range, then f equals f composition, the inclusion map or the identity map on A, and this also equals the identity map on B, composition F. Then subdivision C. Show that this is a bijective function then F composition F inverse is nothing but the identity map on B. In fact, this is what we mentioned in that solution, and this is the identity map on A, and finally there is this subdivision. Show that if X and Y are disjoint sets, okay, so disjointness is a condition, and F from X into Z and G from Y into Z are functions Note that now we don't have f from x into y and g from y into z. Now both f and g have their ranges equal to z, although they have the different domains x and y respectively. Our functions then there is a unique function h from x union y into z such that H composition, or I won't have space for writing this,